Hi everyone, you're in the part 4 of the modeling lesson in Alias. In previous lesson we made a top part of the spoon and chamfers, and in this one we will finish the model by making the bottom part, which is missing right now, and filleting the edges. If you missed previous ones or want my file as a base, check the description down below and download the wire file. Right, so let's go now and build the bottom part of the spoon. So first of all, I will delete the template for our original chamfer. We don't need that anymore. And then, we need to cut this surface, which is our chamfer, pretty much the same way as we did it when we did the top part, because if you remember, as it is continuous on both sides, I will not be able to construct a surface using the skin tool. So I need to separate it. And as I mentioned in the previous lesson as well, for the top part we used only 2-degree curve. So on V direction we have only 2 degrees, so 3 points, 2 degrees, and it has a really limited amount of motion. For the bottom part, I want to bias a little bit the handle so it will not be too archy, right? So I want to kind of eliminate some of the bulge and make it a little bit flatter. And probably I would like to make this portion of the back of the spoon a little bit wider, and for that I need additional control vertices. But the general approach when you really need more is that don't bring it right from the get-go. Start with minimum amount. So here I had 2 and I will bring 2 by default, adjust, and then bring other ones. On top of that, I will probably do a little bit different cuts, because as the bottom part has there is a bigger distance, so the curve will be longer, and because of that I believe that this cut will not make it. So if I'll do the same cut here, I won't have enough control to perfectly create the proper balance. So what I will do in this situation is I will insert my curve and surfaces to perform a cut much earlier. So probably somewhere here, for example. And on the bottom, or on the end, oh my god, on the end of the spoon, well, probably at the same position, right? So let me delete this. I don't need that. Trim. I'm using trim command, the same as in the previous examples, previous lessons. Isolate skin. Delete the history. Bring 1 additional degree. So basically there is a 1 hole in the middle. For now, we will bring more. Delete this part. Use pick CV hole, or you can just manually pick all of them. It doesn't matter, and drag them down. Oh, it's a little bit slow. That's because of the tessellation tolerance. Let me just make it a little bit faster. Okay. So what I'm gonna do now is I will use the patch precision tool. It is in the object edit, I believe. I already used it, but let me just patch. Yeah, it's in the object edit. Here it is. So patch precision, as I explained in the previous lesson, it gives you these curves and surfaces which follows the UV parameterization of the surface. It will give you a center line, parametric center of your surface, which is very handy. Now I will create a line like this, and I will bring, no, not like that, sorry. I will create the line, just random line like this. I will bring 2 degrees and I will align it like this without a scale. So that will be my guide. And by moving the CVs of a surface, I will guide this curve and see where it's pointing. I want that it points somewhere closer to the edge here. And this is important because if I will not do that and I will, bias it somewhere here or somewhere there, once again, there is a really long travel distance and there will be more than, one additional degree. I will probably have a distorted surface here. Really aggressive distortions will be difficult to control. So I will use this approach, and I will just move CVs and start sculpting. Now, as I have only one CV here, I just, for now, just using the transform tool without CV modification tool, CV transform tool. So just casually moving things around, up and down. This one go down a little bit, like this, and this probably. Come on, where you go? Nah, maybe this one is just too close, just like that. All right, so at this point, I will bring CCRV, curvature tool, to inspect the curvature. And obviously, we're going to see that it doesn't really work for me right now. So I need to adjust it the way that it actually gives me relatively decent. Now I'm using the CV transform tool because now I need more precision. Let's put it like this. Now, right now I'm looking at everything. I'm looking at the curve. I'm looking at just the line here, what kind of a character I have. I'm looking at this part. So I'm just, well, basically sculpting. Let me try to aggressively bend that. Oops. Let me see that we are on spot. We do, and that we can proceed. So as you're gonna see, we have quite a decent, uniform acceleration, and then here at the peak it starts to accelerate rapidly. Now the reason why it does so is because here we have two control vertices pretty close together, and because they're too close, that gives you this additional parasitic torsion, which can lead to kind of issues, issues with our with our edge. So our edge, because it is so sharp, it probably will have like a lot of tension, but because I draw with that sharp, I can't blame anyone. I just was my design intent, which means that I need to deal with that one way or another. And I will start. I will keep, I will keep tweaking. So let me just see. Let me just actually rebuild this curve. I'm sorry. So I'll create a new one. I just need to make it a little bit longer, like this. Just made it too short of a curve. Right. Okay. And why 3 degrees? Holy shit. 2 degrees. All right. And I'm always using the auto scale. It basically calculates the spacing, the tangent, a length and curvature length automatically based on the curvature and curvature rate of this current surface, and it does a really good job. In most cases, it does it better than you as a human can do. So let me put it back down here, maybe a little bit more. Still a little bit more. We still have some wobbling here, and it's probably I just overdid it. So let me do like this. Come on. In the other direction, please. All right. So what I see right now is that the curve itself with this edge just doesn't really want to go straight in, which means that just because of a sheer size and proportions of the surface, as well as the tight edge here from this portion, it wants to accelerate. And because it wants to accelerate closer to the end, I will basically let it do this acceleration. The only thing I will minimize the rate of that, but I don't want to do it like this because it will go accelerate and then decelerate and accelerate again. That will look like an error. And as I don't have any additional degrees on my surface, that will be the most natural portion of the stuff as I can get. And you're going to see this distance which we have here. So it's relatively close, but that means that when I construct another surface, so another curve, the actual curve, which will go right somewhere here, it's supposed to absorb this distance. So the further away I place it, the smaller the discrepancy will be. So what I'm gonna do next is, as this is basically as good as we can get with the current set of control vertices, which I actually like. Maybe actually, wait 1 second. Let me actually make this one a little bit maybe higher up, like this. Let's check. This, and let me actually maybe move that still a little bit like this. Completely forgot to increase the scale. Yeah, right, like this. So actually we have yeah, we have quite an aggressive let me work on that a little bit more. And now it goes a little bit away from that. That's, sorry, that's fine. Closer. Now, don't look at the fact that we have this kind of, you see this curve, it just aligns to that on the very, very edge. And this is the reason why we are not doing that. And that's why I said in the beginning that we use all of this part and trying to adjust it this way just to get closer to the proper point so it will curve in the proper direction. Probably like this one. So I leave a little bit of acceleration on this point. I will not dive it down. So something like this. Right, I believe that that's closer actually. So, okay, I'm fine with that. Now, I will do another curve. And let me just pick that. And I will do the same. So I will bring 2 degrees. Oh, sorry, 3 degrees. And I will align that as a curvature as well, but much further than the original one. Because we'll be cutting all of this, we don't care about this position. What we're caring about is we're caring about the... come on. Come on, pick it. All right. Okay. So now what I'm gonna do is I will try to balance the curve the way that it will form me an accelerated curve. You see what's going on right now. So we have this slight deviation here. This is totally fine. But as you can see now, the curve goes, and as this one has a much longer and bigger distance, it will absorb the discrepancy between, you know, the fact that we have such a tight nose and such a deep and, you know, big scoop. And now I really want to have a little bit of a acceleration towards the end, so it will accelerate a little bit, just a little bit more, so that the acceleration not decreasing at the end, but starts to increase. Maybe somewhere here. Right. You're gonna see how further the cut will be for this. Well, actually not really that far, but it's further than the original one. All right. So from the look of it, it looks all right. Now, before doing anything, right now, I will go in and I will bring another control vertex as I promised. Now, when you look at this from the top, you're going to see that we have this surface structure basically, and then the curve, you know, kind of spreads away. You're going to see this right here from the side. Now, somewhere from here. And then it just kind of does this kind of a wobbly character. Now, that's because of the fact that when we extend the chamfer, we basically we biased the edge, and it basically takes this and absorbs this into our surface here as well. Now, it doesn't mean that this is bad. It's actually quite decent thing to do, but that means that somewhere here, you know, somewhere here, there's the, you know, there's the point. So somewhere here, it's supposed to start to bend inwards. So this acceleration, which goes in this direction, right? So the tangent direction will be this one. It's supposed to curve inwards. And that means that here we probably will have somewhat like a little bulge because of we have these pointy nose. But once again, this is the nature of the shape and the nature of the design. Our goal here is to probably make it a little bit thicker on this. So what I'm gonna do is I will use symmetric modeling. I will take one of the CVs and try to extend that away like this. Now, the reason why I'm doing that is because I want that my bottom part here, you see from this angle how, you know, archy it is. So it doesn't have a character at all. So I will make it a little bit wider on this side because I want that it will be a little bit different. Same I'll probably do with these ones. So I kind of bend that towards the, you know, kind of make it a little bit flatter on the side. And but what's more importantly, and that's the reason why I actually decided to create more control vertices, because I want to make these ones much wider. So I will use probably take all of them like this. All of them except the last one. And then I will move them like that. Let me check. Yeah, that's much better. Because otherwise it will be really like whoop like this. All right. Let's look from the top. Now this is probably a little bit too aggressive. So probably I will, you know what? I will probably turn that down a notch. All right, this one is fine. This one is fine. This one is a little bit maybe. I'm looking at the edges right now here. Probably I will keep it as is. Now, I don't want it to touch this one right now, although maybe a little bit. Sorry, wrong direction. You know, the wider I made it, the more curvy it will be and the more pointy, so the more aggressive the, you know, transition will be. So I'll probably keep it like this for now. And start building the transitional surface. So let's see what we came up with. So I will insert the curving surface like that. Let's trim. Let me see that it's just definitely on the edge. This is important, and it is not. Okay, actually no, it is. It is. Now don't look at this discrepancy. That's because of the, you know, tolerance of the curves. The curve itself is actually right there. So as you can see, kind of pick it up. So it's a visual imperfections. So let me insert the current surface. Are we inserting the current surface? Yes, we do. And I will delete this one. I will trim and then duplicate. Okay, so I extracted this edge. Let me set the pivot somewhere here. Scale that like this, and then I will place it somewhere here. Now I probably will not scale that. I believe there is no need, so I will just pick the 1 point somewhere. Let me just align that. Let's see, maybe. Probably somewhere here. So let me bring 3 degrees and let me try to project. So as with the other parts here, these sections from the top, on the top part, I will project curves, not curves and surfaces. I explained in the previous lesson why I did that. So now I'll hide this and I will create a square. 1, 2, 3, and 4. All right, let's see how it goes. So let me project G2. I'm projecting on the Z direction. We are having tangency deviation here right on the edge. I wouldn't say that that's because of the trimming. I would say that's because of the these CV is not, you know, collinear. So we'll fix it a little bit later. Let's look what will happen when I will project this one. Will we have positional deviation here or not? And we have a positional deviation. Well, that means only one thing, we just don't have enough degrees. So let me increase this to 4, delete curve and surface, and reproject that again, like that. So now we have curvature, tangency error, we don't have positional errors, that's good. Now we will use the symmetry plane align and fix it this way. So now it's supposed to be, oops, sorry. It's supposed to be curvature here, and curvature here. Now in the previous lesson I explained how the mirror plain line works. Basically makes the surface, collinear. The first row of CV is collinear to its counterpart, which is supposed to be symmetrical, which is really handy for these kind of situations. Now let me project curves and surfaces here and here. But come on, what are you doing, Alias? Yeah, okay, it's all good. Let's trim, and we have our nose. Well, right from the get-go, I see that. Yeah, we have this lip here. We have this lip a little bit kind of bulging in a wrong direction, very minimally, but it's there. So we're gonna see this here from the top. Now it's all good here. It all goes right, and then the very end, you're gonna see that just starts to kind of rotates in the other direction. That means that here, so basically it goes, and then it just kind of get this kind of negative acceleration. Now this is not the end of the world. This is actually legit. A lot of people will think that this is your design intent. That wasn't my design intent, but it's close to what it is and what I wanted. So that's fine. I will leave it as is. And remember, when you do your first iteration, basically from the sketch, errors will happen because in a lot of situations, like, I'm making these cuts, I'm guessing where it's supposed to connect. So in the situation like that, what I'm looking at is like, okay, when I will be doing a next iteration or I will be doing an A-class pass, I definitely move the span from this point to somewhere here and shift this one somewhere here. So give myself a more breathing room, and then I will probably make this nose just a tidbit wider, and then I will eliminate this in no time. It will go away. So, but for what I have right now, it's a pretty decent result. So let's keep going. And I just want to mention that when I did the same spoon for the preview to the video, and we will get back to this spoon in a minute, I spent a little bit more time than I spent on this one. I really don't want you, just me doing this, 3 hours straight in complete silence. I believe it's not fun, but I hope that you get the understanding of how it's supposed to be done and how I'm doing that. All right, let's go to the back part. I already tweaked it, so it's less pointy. It's still pointy, but less so, which is good. And now let me basically do the same as I did with the top part. And I will, where's my chamfer? Oh, here it is. So I'll untrim my chamfer. I will trim this part and do the same thing. So duplicate, you already know what we will do. So scale that. Wrong position, this one. Set the pivot here, snap. I probably will not scale it also, so I just let it be. Project it somewhere here, maybe here. Yeah, probably. And well, I'm sorry guys, I just completely forgot. I didn't really build, I forgot to build the curve. I thought I did it, but I didn't. So let me build the curve first. Sorry, revert. Now we will save this, don't worry. So we just need to tweak the positions a little bit because we didn't do that. So here we have the end, and you're gonna see that it kinda doesn't really work right. Here we have the outer scale G2, that's right. So let's focus on these control vertices. I'll move that, oops. Let me just, Now I really want this to go down. Now, one of the benefits of the spans is that I can do whatever I want with this. I'm not losing any continuity here because it doesn't affect these ones. The control vertices within the span has a limited zone of control because of the voice they have, because of the basis function by, you know, the Cox and de Boer who developed that. And that's intentional. So I'm looking at this stuff and I'm thinking, like, should I really increase the acceleration or just, you know, let it peacefully come to an end? And actually, I'm just can't decide what I'm gonna do with this. I don't remember. I believe on the original spoon I made more of a accelerated, you know, punch here. But you know, let's just make it more gradual and uniform. Why not? Probably something like that. Okay, let me reposition this one. I don't know, will it turns out to be good or not. From the look of it, it may have an issue because you have such an aggressive turn. And we have these, yeah, and we have these, and probably it will make it too pointy now. All right, let's see how it goes. So let me project. So project on Z curves. Now let's use the curated because I forgot to increase the amount of degrees. Let's say 3 degrees. Let's create a square. Okay, here we go. Just all right, let's see how it goes. So let me just delete this and let me project on Z direction. Let me do this one here. We have a position deviation. Let's increase the amount of degrees. Bam. And then let's project again. Now we have a tangency deviation. That's okay. That's probably the pretty wrong position for the curve. Yeah. Yes, it does. Now, at this point, when I'm looking at this stuff, I'm like, okay, this is the wrong point. I don't want it to be here. And what I'm gonna do is I will just mark it here where it was. And then I will just reconstruct this. Again, sorry, but this time I will reposition this. So that means as I have gap, it means that it's just not enough control vertices, and that's because it covers pretty significant ground. So what I'm gonna do in this case is I will shrunk it a little bit like this, and then repeat the process, and probably somewhere here. So the shorter these one, the more chances that I will achieve continuity, but at the same time it means that this part will be cramped and we may have this additional pinching, which we actually don't want. So I'm still looking where the original position was, and I'm trying to probably avoid that, maybe somewhere here. All right, let me trim this, and let's bring 3 degrees, and let's project again. All right, we have a deviation here. That's okay. We will see how it goes. Okay. Now let me delete this, and let's project. tangent deviation right there. Additional degree. Here we go. Now let me use the symmetry plane align again. Flip it on the other side, and that's it. So let me now project current surface on the Z direction. What, you're measuring something else, aren't you? Yes. And then we will trim. And let's take a look what we have. No, it's actually quite decent. Now you see these wobbles, but that's actually because of the tolerance of a tessellator. Yeah, that's actually quite decent. So good. Oops, what do we have here? That's yeah, that's probably an issue. Let me see. Wait a second. Oh no, it's not. Oh no, there is. So wait a sec. So let me zoom in and see. I didn't check the that's what it is. All right. So let me tweak it a little bit. I'll delete the history, activate my continuity checks, take this control vertex. Now, because we projected it from the Z direction, yeah, and not because of the normals, the control vertices may be not in the position you really want them to be. So that means that by moving these control vertices up and down, we change the character of the surface, but it doesn't really impact the continuity. Well, to some extent. So let's try. See? Maybe a little bit more. All right, and this one definitely will impact the continuity, but we will try to move it just slightly. All right, that's better. But probably we need even more, but I believe with this amount of degrees, we will lose continuity. No, we don't. Let's maybe a little bit this one. Oh, yeah. All right, that's better. Check. All good, nice. Oh yeah, that's much better. All right, that's cool. Great. So let me increment and save this, and it basically save it with a 40001, as you can see. So now what I'm gonna do is I will finish the model by adding fillets. Now, just a little bit about the production and things, because people tend to do, the newcomers tend to do fillets everywhere. Now, in reality, for the rendering purposes, this is totally legit. If you need a good render, path traced render in Octane or, Redshift or, Blender Cycle, whatever, pick your poison, then of course it's really important to have the proper geometry there and not, fake layer weights or fake normals, which sometimes you actually need to do anyway. But and it's good for the renders. But in real life, it's more about the matrix, and die, or depends on the type of a production. Like if you have a really tiny fillets, they will not help you when you do a matrix, because it won't help you pour the model out of the matrix, even if you have the proper draft angles. And the actual shear size means that you need an extreme machine precision. And when it comes to the mass production, that's rarely the case, because we just it's at stamping, pressure casting, depends, and it's not really that accurate as EDM machine. And in our case, the fillets will be tiny, so the radius of a fillet will be around 0.2 millimeters. So it's more for the show. In reality, it will have no fillets. When it will be prepared to create a matrix from it and finding the parting line, there will be no fillets on the model. And then the product will be sanded and you will get the proper, highlight on the edges. So that will be a different process a little bit. But Once again, I said that we will do the fillets, and we will do the fillets, for example, for the rendering purposes, and that's why there will be probably two models, one for production, one for visualization, and we will do the version for visualization. So let me untrim this and delete all the curve and surfaces. So these one here out, these one out, and then we will flip on the other side like that. And a good rule of thumb actually about the fillets is you do, if this is a symmetrical model, do the one part and then do another part. So because I'm going to cut it on half, but it takes quite a lot of efforts, because when you do fillets, you most likely use a Bezier surfaces checkbox. That means that instead of a multi-span surface, it will be a single span chunks, and that just give you a more convenient, more accurate result. Faster, but that's a nightmare to project everything on the other side. You need to literally manually pick every edge and project, which is a pain. So just to save ourselves some time, I will try to do it, and I believe I will succeed, because it's a pretty decent surfaces. They are pretty simple, and they are positional, and they are have a proper angles everywhere, so it's supposed to work. But in reality, you rarely do it as a whole. I will do it as a whole. So the start and the end, I will probably leave it default, because here on the edge is tangential here and tangential here. So it's supposed to work just fine. I will use the radius construction type. Now there is a difference between the radius and the quarter length. It's just the way how they construct it. The radius give you the radius, and based on the angle of the surfaces you want to create the fillet from, the radius keeps the same, stays the same, but visually it will look like your fillet become to be smaller and bigger. And the quarter length alternatively make it visually represented as the same width, but in reality it will have a different radii. Well, I will use this just a standard one, and I will probably do the top and the bottom different. It's a common practice just to bring a little bit more interest to the model, although here probably doesn't matter. So I will use, I don't know, for the lack of it, let's say 0.2 supposed to fit. The form factor 0.5 tangent, it means that it will have a little bit more acceleration than just a regular, radial fillet. And I will just pick all these parts, and then these and these at the same time, and hit spacebar and pray that it will work. And it does. Yeah. So first of all, what we check is we check tangency here. It works. And on this part, it does. Cool. Now let's do the bottom, and we basically do the same. I will use the radius type fillet. Select everything here. First one, second one, and I will type it. As I said, let's make it smaller. Let's say 0.1. And here we go. All right. And that's it. So if you get that far with me, well, congratulations. I hope you learned something from these lessons. Now, so it's kind of the end for the modeling of the spoon, but this is not the end of this particular lesson, because if you watch my original lesson, my first lesson on this series, the first part of these modeling lessons, or you just paid attention to the preview of these lessons on YouTube, you will notice that this spoon missing one crucial component. And I mentioned that I will get back to that at the end of the whole series, and here we are at the end. So it's missing a pattern on a handle. And let me open up my spoon which I made for this lesson. Here it is. And you're gonna notice that it has this pattern. Now, it doesn't have fillets here. I do fillets by sculpting, and this pretty common tactic when you need to have just a lot of T edges and star edges and stuff like that. But the actual pattern is not obviously manual. It was designed in parametric modeling tool, basically programmed. It is a script which works with a geometry. It creates me the proper geometry, and then I will bring it in Alias. So the reason why it's not in the Alias modeling lesson is because it's not a modeling in Alias. I did it outside of the Alias. And as I promised, I will go and quickly explain how I did that. You will quickly understand why it's not, full description, because there is a lot of stuff going on. But I just want to give you the general sense of what it is, and if you find yourself interesting, you just kind of let me know in the comments. So for everyone else who's watching till this moment and not really interested to that, well, once again, thank you very much. I'll see you in the next one. And for all the other people, let's just jump into the rhinoceros and grasshopper. So here we are. So the general premise with parametric designs, where you need a lot of repetition or the specific mathematical relationship between the shapes, is you do your part, your classical modeling approach, like in Alias, in I don't know, Fusion 360, Rhinoceros, whatever, and then you bring it some parts of this model which you want to enhance in a parametric modeling system. Now, one of them, and the most prominent one, is you're probably familiar me using, because I really did it a few times on this channel, is a Grasshopper. Now, Grasshopper is a parametric modeling tool, which is latches on. It doesn't have its own viewport, so it's latches on the software, or a couple different softwares. One of them is Rhino, and a lot of people using it with Rhino, because Rhino, for a few years already, has the Grasshopper built in. You see this icon, and it's basically already within a Rhinoceros, which is amazing. And a Grasshopper is a standard these days in the industrial design and architecture, because Grasshopper can work not only with the CAD data, but it can work with polygons as well. So yeah, it's pretty powerful. It has a really logical structure. The data management here is amazing, and if you know the basics of programming, you'll be right at home. It's very easy and really powerful instrument. So how I actually do this, what's the process? I will go to Alias here. I will pick the surfaces I'm looking for. Now I want a pattern, a seamless pattern, starting somewhere from here and goes right to the end of my spoon. So I need this surface, and this surface. I select the surfaces and I will go to File, Export, and I will export it as a step file, this one. Now this is the standard 1214, kind of old algorithm, but very stable one. And then I will go into Rhinoceros and import it in the Rhinoceros. So this is the viewport of the Rhinoceros. If you're not familiar, this is the viewport of the Grasshopper. And when I bring this data in, I will create an additional surface which covers all of these pieces, and then throw everything into the script. So this is the script which actually does work. Now, the reason why I'm not really explaining how all of this works in the detail, because there is quite a lot of stuff. And all of this design, you're going to see this, my Cyrillic, I'm Russian, so this is, my descriptions of what the hell is going on here for myself, because, sometimes you're not doing it for months and then you get back to your script and like, what the hell is this? So, and yeah, it's keep going, and keep going, and keep going. It's not ended, and it's because, yeah, this is the final end. This is the end of the, this is the edge, and the curves themselves are probably here. Here they are. Oh, this is the curves now. The surfaces are here they are. All right, so as you can see, this is quite a big script. Now the bottom one is for hexagons, this is for diamonds, but the general premise is as follows. I create a collection of points on one big surface which hugs everything else, all the collection, populated with points in the pattern of hexagon, or the diamond pattern, so basically in the form of diamonds. And then I will project every point in a specific direction, in the proper direction, on the surface where it is. Now the main problem with with the patterns which goes through the multiple surfaces is that every single surface has its own like localized parameterization, and you can't really just take and do it automatically across the board. You need some kind of a mediator, something in between, to make it work. So, and that's what I did. So there is a big cushion with the proper points which are spread properly, then that all of that shoot down on the proper direction on the actual surface, and when it lands, I will collect when it lands. It will give me the same points with all the necessary data, the vector directions, the curvature values, the actual position, 3D space, position, and UV coordinates, everything I need. And then I will construct through these points, I will construct the lines, and then I will use the rail tool or a square tool. We actually have them in the Grasshopper, and construct the surfaces. And then I will do additional attractors, so make the, the size like of the, protrusion bigger or smaller based on the proximity of the other stuff, and so on and so forth. And the reason why this script is so big is because there is a lot of things it does behind the scenes, and it can do a lot of different patterns, not only diamonds, and it can do conics. So if the surface is a conic surface, or it can do the understand the closed geometry. It understand does your objects has holes and you don't want the pattern there, or you want to use that as an attractor, and a lot of other stuff. So this is more like a combiner for me. And I have plenty of these things for my own use, and that's the realities of this. If you try to get into the parametric modeling, it's really fun. It's really cool. It's not that complicated as it may seems, but there is no ready solution in the internet or on the in the plugins who can do what you really need to do. In most cases, you need this holy grail, an ability to construct patterns across multiple surfaces, and that is like a test for proficiency. Every single designer will grind it down until he figures out how to do it. And all of the scripts are custom and very specialized. You can't do one big script for everything. Alternatively, we already have the systems, but they does not exist because this is a pretty tricky subject. Well, and that's why I'm not really explaining everything here, but this is how it works. And every pattern on every CAD model, if you ever saw, in real life, well, trust me, it done the same way. So it's probably done in the Grasshopper or in Dynamo, most likely in Grasshopper, and it has a huge script behind that which actually do it. Now, the question to you, do you really interested in this or not? If you do, then I can run a new series about parametric design, start fresh, start new, and basically give the general goal to explain you how to create patterns across multiple surfaces, any pattern, whatever pattern you want. And it just takes some time. It's kind of slow process. You need to learn data management first before you do so. If you're interested, let me know in the comments. If you're not interested and you want more Alias, let me know in the comments as well. This is really helpful for me and to understand what guys you really want. And I already talked a lot, so thank you very much for getting to the end. I hope you learned something new. If you have any questions, or you have or you're struggling building something, or you have some issues with your model, once again, let me know in the comments. I'm always reading them and asking and answering your questions. All right, thank you very much for watching. Thank you very much for spending your time, and I will see you in the next one.